Hello, hello, hello. Okay, so man, I'm looking at today. Today we got a stacked day, and actually the next week, really the next 3 weeks are gonna be totally crazy. That's okay. We're all good. We're all good. I can take the crunch. Um. Okay, so today is on 5.6 of linear algebra and its applications by Lay. Discrete dynamical systems. Let's just look at the exercises. Okay, so we definitely need to read this section because I don't know exactly how to do that. I mean, surely it's that you can like use the eigenbasis or the eigensystem as a way to find, because I need to get shorts. It's already getting hot out. Okay, but then the next is 3 by 3. Find the solution. Okay, describe what happens is okay. So then in this case, um, what would I do? I would look and I would look. Okay, so I would check if this is, so see, it's not an eigenvector. Yeah, okay, so we definitely need to read this section because I actually don't know this stuff. Okay, there's not that many exercises, which is good. All right, then, wait, let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so a pretty long section actually. Eigenvalues and eigenvectors provide the key to understanding the long-term behavior or evolution of a dynamical system described by a difference equation. Such an equation was used to model population movement and will be used in Markov chains in section 5.9 and the spotted owl population in the introductory example. The vectors xk give information about the system as time denoted by k passes, where k is a non-negative integer. In the spotted owl example, for instance, xk listed the number of owls of 3 age classes at time k. The applications in the sample focus on ecological problems because they're easier to state and explain. Say problems in physics or engineering. However, dynamical systems arise in many scientific fields. For instance, standard undergraduate classes in control systems discuss several aspects of dynamical systems. The modern state space design method in such courses relies heavily on matrix algebra. The steady state response of a control system is the engineering equivalent of what we're calling the long-term behavior of the dynamical system. Okay, it doesn't really mean much to me. Until example 6, we assume that A is diagonalizable with n linearly independent eigenvectors and corresponding eigenvalues. For convenience, assume the eigenvectors are arranged so that they're decreasing. Since v1 to vn is a basis for Rn, any initial vector x0 can be written uniquely as a linear combination of this eigenvector decomposition of x determines what happens to the sequence xk. The next calculation generalizes this simple case examined in example 5.2. Since vi are the eigenvectors, then ax0 is equal to x1 equals ax0. And x0 is going to be, because we know that this is a basis. Okay. Okay, so we take the, yeah, okay, that's cool. Oh, that's really cool. Yeah. So you you can just take powers of the eigenvalues in general, right? There you go. Okay, a predator prey system. Deep in the redwood forests of California, dusky-footed wood rats provide up to 80% of the diet for the spotted owl, the main predator of the wood rat. Example 1 uses a linear dynamical system to model the physical system of the owls and the rats. Admittedly, the model is unrealistic in several aspects, but it can provide a starting point for the study of more complicated nonlinear models used by environmental scientists. Denote the owl and wood rat populations at time k by xk equal to OR. OK, RK. Owls and rats. The wood rat. Freaking creepy little wood rats. Where k is the time in months, OK is the number of owls, and R is the number of rats. Okay, suppose that we have where P is a positive parameter to be specified. 0.5 OK in the first equation says that with no wood rats for food, only half of the owls will survive each month. While 1.1 RK says if there's no owls, then the rat population will grow by 10%. If rats are plentiful, the 0.4 RK will tend to make the owl population rise, while the negative term minus P OK measures the death of rats due to the predation of owls. In fact, 1000 P is the average number of rats eaten by one owl in 1 month. Determine the evolution of this system when the predation parameter is 0.1. Okay, we get when the eigenvalues of this coefficient matrix A for the equations in 3 turn out to be lambda 1 equals 1, lambda 2 equals 0.58, and then we get the eigenvectors. An initial x0 can be written. Okay, then we do the eigendecomposition, and we get our solution. It's funny taking these classes at the same time. All right. As k goes to infinity, 0.58k rapidly approaches 0. Oh, so let me think about this. Did they specify that all the eigenvalues are positive? No, they just said that they're decreasing. Because it's going to oscillate if it's negative. But it is going, but okay, so if it's, regardless, if it's between -1 and 1, then it decays to 0. Otherwise, it explodes. Then for all sufficiently xk is approximately the same as, okay, so let me write this. The approximation in 4 improves as k increases, and so for large k, okay, fine. The approximation in 5 says that eventually both entries of xk, the number of owls and the number, grow by a factor of almost 1.02 per month, a 2% monthly growth rate. By 4, xk is approximately a multiple of 10, 13, so the entries in xk are nearly the same as the ratio of 10 to 13. That is, for every 10 owls, there's about 13, 1,000 rats? Whoa. Okay, there's a lot of rats in the woods. Example 1 illustrates 2 general facts about a dynamical system in which A is n by n, its eigenvalues satisfy lambda, the abs value of lambda 1 is greater than or equal to 1, and for all the others are less than, are between -1 and 1. Then and v1 is an eigenvector corresponding to lambda 1. If x0 is given by equation 1, with c1 not equal to, yeah. Then for all sufficiently large k, xk plus 1 is equal to lambda 1 times xk, i.e., this is the best way to write it. Okay, but what if it's the eigenvalue? Do they call it the spectrum of a matrix? Spectrum matrix. I think it's the distribution of eigenvalues, right? Yeah, the spectrum of a matrix is the set of its eigenvalues. I was watching this video on spectral graph theory. All right, which I guess is basically, I guess in more generally, spectral theory is basically the study of, is an inclusive term for theories extending the eigenvector-eigenvalue theory of a single square matrix to a much broader theory of the structure of operators in a variety of mathematical spaces. But is it always on a vector space? Ooh, I love these pictures. These pictures are so good. I don't know what the edges of this graph are, but that's okay. It is a result of studies of linear algebra and the solutions of systems of linear equations and their generalization. The theory is connected to that of analytic functions because the special properties of an operator. Okay, I don't know any of that, but that's okay. Lambda 1 eventually determines the eventual growth rate of the system. And by 7, the ratio of any two entries is going to be the ratio of any two entries in xk is nearly the same as the ratio in the corresponding entries of v1. Okay, here we go. This is what I wanted, a graphical description. When A is a 2x2 algebraic, when A is 2x2, algebraic calculations can be supplemented by a geometric description of a system's evolution. We can view the equation xk plus 1 is equal to axk as a description of what happens to an initial point x0 in R2 as it is transformed repeatedly by the mapping x to ax. The graph of x0 to x is called the trajectory of the dynamical system. Plot several trajectories of the dynamical system. So let's just think about this. Clearly, we have two eigenvalues that are independent. So it's going to be 0.8 or minus 0.8. No, 0.8 and 0.64 are the eigenvalues. And so they're both positive. See, that's actually interesting. It's interesting. The difference between a discrete dynamical system and a linear homogeneous differential equation is in this case the eigenvalues are positive, so it would grow because the derivatives are positive. Wait, let's see if this works now. Oh, nice. Okay. There seems to be a fundamental difference in like a system of linear homogeneous differential equation that you can write in matrix form and discrete dynamical systems, in that if the eigenvalues are positive at all for the differential equation case, then it's growing. But if the absolute value of the eigenvalue is less than 1 for the discrete case, then it actually shrinks. Continuous time evolve like x prime equals ax, where each eigenmode grows or decays as e to the lambda t. Yeah. That's kind of interesting, right? All right. So yes, you can draw. Let me think about this. For any for any diagonal matrix with a non-zero diagonal, or that's not the right way to say it, that every entry is non-zero in the diagonal. Yeah. Right. Yeah, so the straight lines are going to be along the eigenvectors still. That doesn't change. That makes sense. That would be crazy if it, yeah. Okay. Uh, this plot for my book is interesting because it has those lines that connect the discrete points of the trajectory for the discrete dynamical system. And I'm just thinking, how do you come up with the function that describes the continuous time evolution of the discrete dynamical system? Because you can't just do the conversion where you turn x prime equal to ax, because then it's going to grow. Oh, yeah, that makes sense. Yeah, you just take this n. Okay, cool. All right, an example to the origin is called an attractor because all trajectories tend towards zero. This occurs whenever both eigenvalues are less than 1 in magnitude. The direction of greatest attraction is along the line through 0 and the eigenvector v2. for the eigenvalue of the smaller magnitude because we assume that the eigenvalues are decreasing. Okay. But wait, if it's like -2, do they have one where it flips around? Oh, did they show me? Was it in there? Oh, that's so cool. Okay, that's great. So that's easy. So, okay. In the next example, 0 is called a saddle point because the origin attracts solutions from some directions and repels in other directions. All right, cool. This is the exact same as what we've seen. So, the preceding 3 examples involve diagonal matrices. To handle the non-diagonal case, we return for a moment to the n by n case in which eigenvectors of A form a basis for Rn. Let P be the columns. Let P be the matrix of column of eigenvectors. Let D be the diagonal matrix with corresponding eigenvalues on the diagonal. Given a sequence xk, satisfying xk plus 1 is equal to axk, define a new sequence yk. Substituting these relations into the original equation using the fact that A equals PDP inverse. Py k plus 1 is equal to APYK. So we get P. Oh, okay. Yeah. This is such a roundabout way to just say that you did this change of basis onto the eigenbasis. All right, left multiplying, because these are coordinates with respect to the eigenbasis. Left multiplying both sides by p inverse, you obtain yk plus 1 is equal to dyk. If we write yk as y of k and denote the entries of by y1 to yn, the change of variable has decoupled the system of differential equations. The evolution of y1, for example, is unaffected by what happens by y2 to yn. The equation xk equals pyk says that y of k is the coordinate vector of xk with respect to the eigenvector basis. That's what I was saying, bro. We can decouple the system by making calculations in the new eigenvector coordinate system. When n equals 2, this amounts to using graph paper with axes in the directions of the two eigenvectors. Show that the origin is a saddle point for solutions. I didn't know about this though. This is pretty interesting that like the natural way that you would make the discrete dynamical system continuous does not give you the linear homogeneous differential equation. They're different. When a real 2x2 matrix A has complex eigenvalues, A is not diagonalizable when acting on R2. But the dynamical system is easy to describe. Illustrated the case when the eigenvalues have absolute value 1. The iterates of a point x spiral around the origin along an elliptical trajectory. If A has two complex eigenvalues whose absolute value is greater than 1, then 0 is a repeller and iterates of x0 will spiral around outward around the origin. If absolute values, but what if 1 is Um, oh, right. The fact that they come in conjugate pairs is really sick, actually. I don't. Recall from this chapter's introductory example that the spotted owl population was modeled by. Okay. MATLAB shows the eigenvalues are approximately 0.9, blah, 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 blah. Observe that. Is there hope for the spotted owl? Recall from the introductory example that. All right, cool. That was a pretty lightweight section actually. There wasn't a ton to that. The only cool thing is that stuff about the ways to convert a discrete dynamical system into a continuous system. And it's kind of like there's like two natural ways to do it. There's like the first way, which is just say x of t is equal to a to the t x. Wait, hold on. This is how to compute the log. Really? That's actually wild. So this is the discrete version. Two natural ways to take a discrete dynamical system into a continuous. X prime equals ax and x prime equals log ax. What continuous system has the same time one map as the discrete rule? Yeah. Very interesting. All right. Right, because yeah, it makes sense that it's log. It makes sense that it's log because log of 1/2 is going to be negative. So that's really interesting. Okay, so we'll do the practice problems. We'll read through the problems. Hopefully, we can do this section relatively quickly. I usually budget myself like 2.5 hours or 3 hours to do a section of linear algebra, but this one seems pretty quick. All right, but I'll be back. Okay, let's figure this out. I feel like a lot of these problems, maybe there's only a couple of theory problems. Seems all applied. Probably be on a test, but it's like the theory at this point is what's way more important to me personally. So to compute this, you basically solve you do a linear solve of eigenbasis for this. So if we have oh, we need to start this thing up. I like having multiple computing environments. Like having this one and Julia. Because Julia, it's easier to write the matrices, which is kind of funny. You know, I never got to finish 5.4, but 5.4 is the best section in the book so far. If you're going to learn linear algebra, understand 5.4. This section rules. Okay, but let's go back to our problems. All right, 1 minus 1, 1, 1. A is equal to 1 minus 1, 1. Okay, and then we have x0 is equal to 9, 1, right? Let's do this. 9, 1. Okay, that's cool. So now what we can do is we can do linear solve a for x0, and we get 5 minus 4. And what that means is, yeah, I'll do it. I'll actually do it on paper so that we can get a set. I'll compute the eigenvalues and stuff like that, not on paper, just for the sake of whatever. Okay, so I gotta tape up my cam. Hold on. Okay, sorry about that. Let's do this. All right. So this is going to be 5.6, number 1. Oh well, let's before we do all this, let's read through all the problems and then we'll figure out which ones we want to do. So I definitely want to do 1 actually because 1 is good practice. So 1. 2 is also pretty good actually. And they give you the eigenvalues and eigenvectors, so that's not so bad. And they want you to know that they're getting hung up on this thing of like, if there's one that's big, then you can write the solution, you know, for large K as just this. All right, so we'll do 2. I'll do 2. All right, 3. Assume that any initial vector x0 has an eigenvector decomposition such that the coefficient c1 is positive. All right, determine the evolution of the dynamical system in example 1 when the predation parameter is 0.2. Um, okay, we'll do 3. I end up just writing down all of them. 4, let's just skip 4. I don't really care about that. Unstable equilibrium. Tawny owl is a widespread breeding species in Europe that mostly feeds on mice. Suppose the predator-prey matrix show that if the predation parameter is 0.15, both populations grow. I mean, you just plug in for 0.15, you calculate the eigenvalues, you show they're greater than 1. We're going to skip that. Show that if the predation parameter P is 0.3, both will eventually perish. Okay, so I mean, it's literally just compute the eigenvalues. I mean, the spectra tells you so much about the long-term behavior. And it's not that they're less than 1, not make sure that it's okay, maybe if there's a couple of complex eigenvalue ones, we'll do the complex eigenvalue ones. Determine the nature of the origin. Okay, so it's just equilibrium points classification. We can skip all of these. They're maybe some of these are complex, but I'm not really keen on figuring that out. This one's kind of interesting. A is a 3x3. We're given 1 eigenvector and 2 eigenvalues. Construct the solution of the differential equation as in the one time step form that satisfies x0 We'll do 15. 15 is kind of strange. I'm not really feeling these applied problems. Let's just get back to 1. Okay. So we can hop over here. So we have a 2 by 2. Okay. Lambda 1 equals 3. Lambda 2 equals 1/3. Then we're given that V1 is equal to 1, 1. V2 is equal to minus 1, 1. X0 is equal to 9, 1. Okay, and what we get is that if B is the basis, V1, V2, then X0, B is equal to the matrix B times the matrix B times this is equal to X. So then solving for X0, B is equal to B backslash X is equal to, and then what did we get? Let me just go look. We got 5 minus 4. Okay, so what that means is that we can write X0 is equal to 5V1 minus 4V2. And then if we want to compute A of this, A, then we're going to get AX0 is equal to A times 5V1 minus 4V2. Okay, then what we can do is just using the property of a linear transformation, we can say that this is equal to 5AV1 minus 4AV2. But AV1, we know that these are corresponding. So we know that AV1 is equal to 3V1. So this is just going to be 5, 3V1 minus 4. And then this AV2, it's 1/3. So this is going to be 1/3 V2 is equal to AX0. So that's really the whole solution there. This is X, so this is X1. You can do all the algebra if you want, but I don't, or the computation if you want. Okay, B. So this is part A. Now B is find okay, so let's just so here's how we should think about this. Let's say that we have x1 is equal to 5a v1 minus 4a v2, and we apply a again. We're going to get x2 is equal to a x1 is equal to 5a squared v1 minus 4a squared v2. But we can just write this since we know that this is going to be wait. Is equal to 5 times A times 3v1, and that's going to be equal to 5, 3, A v1 is equal to 5, 3 squared v1. So what we're going to get is xk is equal to 5 times 3 to the k v1 minus 4 1/3 to the k v2. Okay. And more generally, we get x, whoa, x to the k is equal to but that's for a 2x2 system. Okay, problem 2. Suppose the eigenvalues of a 3x3 matrix are 3 4/5 and 3/5. Okay, to solve this problem, we need to find this solution, which is different than solving it in terms of the eigenvectors. So to solve it in terms of xk, oh, we didn't do the practice problems. Let's look at the answer of practice problem 1. Okay, so you still write it, so you still do a linear solve, so that's fine. Okay, then you get xk, but that's not, okay, so it is the same problem. So what we're going to do is I'm going to ask it to uh, 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 transcribe the vex into mat A, uh, vals into list vals, and x0 into a list in Wolfram. I know what you talking about. Okay, cool. That looks right. Okay, so now what we can do with all this code is we can do linear, let's say, I'll call this xb for x in the basis of the eigenbase, or x is a coordinate vector. Wait, how are you supposed to say this? What I'm saying is that x is the weights that get you x0. So really what we're solving is we're solving for a dot xb equal to x0. So that's what we're solving. So then we can do linear solve a x0. Okay, and we get 2, 1, 2. So now what we can do is just to double check, we can do a dot xb. And we get -2, -5, 3. So there's our double check. We should expect something like that. If that wasn't the case, this would be psycho. Okay, so now that we've written x0 equal to, you know, like xb1 times, anyway, so now we can just do our normal thing. So gonna be problem 2. And problem 2 we have, I'm not even gonna write out the whole matrix. I'm just gonna say that we have the vals lambda 1 equals 3, lambda 2 equals 4/5, and lambda 3 equals 3/5. Then we have A is eigen matrix equal to, you know, like V1, V2, V3. Then we solve XB, or I guess this is going to be XA really, is equal to A backslash X0. Oh yeah, X0 is equal to -2 -5 -2 -5 3. Okay, is equal to, and this is 2, 1, 2. So now we can just write xk is equal to 2 times 3 to the k times, or we'll just write v1 plus 4/5 times 1 to the k v2 plus 3/5 oh wait, I did this wrong. This is to the k, so this is to the k, this is 2, and this is v3. I did it right here, I just did it wrong here. Okay, cool. So that's that problem. Pretty simple stuff. Describe what happens. Well, what happens? Basically the long-term behavior ends up being in the direction of V1. Okay. Determine the evolution of the dynamical system this one's not that interesting anymore. It's just like find the spectra. We say we're gonna do 15 next. All right, let's just do 15, and then we'll be done with this section. Yeah. So this problem is actually interesting because they make it seem like you're not supposed to find the spectra yourself. Construct the solution of the dynamical system using a single eigenvector. Transcribe, but also, how do they want us to solve this? It seems like they don't want us to solve. Because, for instance, if you only get 2 eigenvalues, they didn't say that these are all of them. So that, it could be that there is a third. And that third could be greater than 1. So you can't say that it decays to 0. Okay, that's what I was thinking. So you do take. Okay, so then you find that. So Oh yeah, I forgot about that. The trace is equal to the sum of the that is nuts. I really feel like that's so deep. The trace is equal to the sum of the eigenvalues. So wild. Whoa, I hit the limit? What the hell? Wait, why didn't it didn't make the plot? See, like, what is going on here? X prime equal to ax and x prime equal to log ax is that if we have one eigenval in the log case dd, then we can get a fixed point not at 0 if a is diagonal, because it seems like this system decays into a projection onto a point that is not 0. That's impossible in the continuous x prime equal to ax case, I think. I don't know why they call it the naive case. Is sigma null space? What does that even mean? Oh, this is the image. This is the image function, I think. Oh no, that's the spectrum. Okay. Yeah, actually, the whole difference here is like really pretty cool. I feel like they should talk more about this. Okay, so that is it. We're not going to do these other applied problems because they're boring. So then we are just going to hop into 5.7, right? Yeah. Okay, so I'll be right back.